having already doing his PhD with Paul Charbonneau and Antoine. First time the vessel, so and please, at least we see the sun. That's a cry that we heard from people in the audience.
Thank you so much for having me. It's a pleasure coming at the festival for the first time. And yes, we will talk about the sun a little bit today. It's my pleasure to talk to you about flares as magneto-hydrodynamical avalanches. So, solar flares. Most of you probably know what they are, but the sun community, we're very lucky. We have the pleasure to have pretty good videos of the sun, so it would be a crime not to show some of them to you right now. So what's a solar flare? And this video can be misleading because what you're seeing here is mostly a coronal mass ejection, but most of those events also come with solar flare. So a solar flare is basically just ejection of very energetic particles and photons at the surface of the sun. And here's another pretty nice video of that happening. Doesn't come out so well, but it's still very impressive. And why do we care about solar flare except from the fact that they make for some very cool videos? It's because it's actually a very important hazard or interest for people who do space meteo. So when solar flares reach the Earth, most of them are diverted by the Earth magnetic field and end up as auroras at the poles. But when very strong flares arrive on the Earth, they can cause massive damage. We've had power outage because of them, and because we're exploring we're developing space technologies. A lot of people have developed an interest for solar flare, and especially we work in predicting them. So that's something that a lot of people care about. So in order to predict solar flare or just understand how they happen, you need to look at the mechanism behind them. So understand why they happen. And it was very a surprise for me to learn at the beginning of my graduate studies that even the sun, we don't fully understand yet. There's still a lot of work to do to understand what the process is behind solar flares. So one of the main things that you start to look at when you want to understand the physical process is the statistics behind it. And solar flares are one of the systems that exhibit this so-called scale invariance. So this is a plot of basically you can think of the x-axis as the energy of a solar flare, and the y-axis is the frequency. And this is in log space. And basically what this tells you is that the biggest solar flares, the ones that interest us the most, also happen the less. And the flares that are the most common are small flares. And so this power law is related to what we call scale invariance, because this indicates to us that you can find flares of flares can happen in basically a bunch of different scales. It can be very large or very small. And this picture is just, this plot is just to drive this point where it's basically observations of, we start with nano flares and then micro flares, solar flares, and then on the bottom right of the plot, you have some super flares in sun-like stars. Just to drive this point that this phenomena of solar flare, you would think that the biggest flares and the smallest flares. I need to talk a bit softer because I'm disrupting the signal.
Can I ask you a quick question?
Yes, of course.
I know that some of the nano flare. Oh, that's gone again. I should not have asked the question. Some of the nano flares are looked at through radio emission. Are those the ones there, or you haven't included those?
I'm not quite sure. This study of nanoflares from 2000 is quite outdated, I could say, because a lot of the new observations probably would have constrained this, but I'm not sure. Okay, sorry about that. And yeah, so just to drive this point that these flares, you would expect the biggest flares and the smallest flare to basically be the same phenomena, just on different scales, right? So this is what we call scale invariance. Basically, well, it also hints at something we call universality of the flaring process, which basically means that you have this phenomena that can happen on any scale. So some of you in the room right now probably have heard of this before. It also hints at something that we call self-organized criticality. So what is self-organized criticality? It's this very interesting idea that was developed a few decades ago to describe these systems that exhibit scale invariance. So the idea behind self-organized criticality is you have a system that naturally evolves towards a critical state where small disturbances can trigger events of any size. And you find this scale invariant behavior. And this is very important without the need for fine-tuning external parameters. So these systems will reach this critical state basically no matter what you do. Jensen basically reduced them to these set of three rules that you find in all the self-organized criticality systems, where the system is interaction dominated, the interaction has a threshold, and the system is slowly driven. And of course, it's very easy for me to find good examples. And this example I chose is unfortunate due to what happened this week, but I swear I chose it before I came here. Yes?
That you have all kind of time scale in the system. When you say slow compared to what?
Yes, good question. So when I say slow, what I mean is that the driving of the system or the deposit of energy in the system needs to be slower than the interaction that can destabilize the system. So in the case of solar flare, for example, the flaring happens on a time scale of seconds to minutes, but the time that it takes for accumulating the energy on the sun can be days, weeks, months. So that's the time scales we're talking about. And for example, for forest fires, you have a system that is interaction dominated. So the fire can only spread from a tree to its neighbor, for example. The interaction has a threshold, so you need basically the air to be hot enough, and you need a certain amount of fire, for example, for it to spread. And then finally, the system is slowly driven. It takes a time for the trees to grow back. So you end up with a system that has all the ingredients for self-organized criticality. And then, so this was just a quick example. Another one that we use a lot in solar physics is this so-called sand pile model. Maybe you've heard of this before. And this one specifically, Lua-Hamilton model, is a sand pile model applied to solar flares. But the idea of the sand pile model is very similar to the forest fires, where you have this system where you drop sand on a sand pile. So you drive the system by dropping sand on it, and then the slope reaches a critical slope. And you can trigger these so-called avalanches where sand can fall on the side of the system. So this loops back to the observation of power laws and scale invariance, because basically, if you study the energy that is released in these systems, sand pile models, you find this log, the power law, where you have scale invariance. So you find a lot of little avalanches and a few very big ones. And the idea is that basically this model has the same ingredients that you would expect maybe for all the other self-organized criticality systems. Right. And how does this loop back to solar flares, you might ask? Well, solar flares, you also have all three ingredients. So this picture here is basically the idea that was proposed initially by Eugene Parker for the nanoflare hypothesis. And basically, you can think of this as a coronal loop on the sun, but we basically stretch out both hands to have something that is vertical. But so basically, the idea is that because of convective motion of the cells in the photosphere of the sun, these magnetic field lines get shuffled, and there's a tension that builds up. And then when there's enough tension, because of magnetic reconnection, these field lines can basically straighten up, and that's one of the main theory we think that can explain solar flares, basically. So this also has. So
for the students, it would be good to say that this model is a straightened model of the margin. Otherwise, there will be some Y on top.
Yes, good point. So exactly, this you need to think of this as the coronal loop that you see at the surface. So this is just the straightened version. And so again, you have a system that is interaction dominated, as in the magnetic reconnection is a process that is local. The interaction has a threshold, so magnetic reconnection has a threshold, and it is slowly driven, as in the movement of the photosphere is slower than the time it takes for a flare to happen. So we think that self-organized criticality could be some explanation for the flaring process on the sun. Could be is very important. Again, I thought that I could show a nice video because we have them. And this is just to show that somebody could say, well, why not just like look at the sun and see if you find avalanches, see if you find self-organized criticality. I think we might get there in the next few years, but we're not there quite yet. But we're getting close. And I think, well, this video probably looks better on this screen. But we are getting to the point where we are able to look at these finer scales. But we still don't know if this is self-organized criticality. So what do you do when the observation isn't enough? Well, you go to simulations. And these so-called MHD simulations have been around for a long time. So this is just to show that people have been trying to simulate the corona of the sun for a long time. And what started out with 2D quickly evolved to some nice 3D simulation because of the evolution of numerical power, computing power. And thanks to like recent advances, especially in the past 10 years, we've been able to push these numerical simulations to the next level. And
I might ask.
Yes.
These are 3D MHD in a periodic box, so they're the solar geometry.
I think these are periodic, usually the boundaries, except usually the bottom of the box is it has like a line tie condition or maybe some magnetic configuration, but usually the sides of those boxes, for example, this one is periodic. This one is 2D. I think it's probably periodic too. For the other two, I'm not quite sure.
It's twisted, right?
Yes, in this one, that's what is happening. Yeah, and they're studying basically the release of the energy transfer between magnetic energy and kinetic and thermal energy. And what used to be the problem is if you look for avalanches or self-organized criticality in those systems is if you only have fixed or like few cells by a few cells, it's hard to study this scale invariance because scale invariance happens on so many scales that if you only have like a couple cells, how can you verify if it holds for more than like one order of magnitude? So this is why recent advances are really unlocking this next level where we can really look at like different scales.
You just ask what
Honestly, I'm not quite sure. I think I haven't studied this simulation, but I don't think that this simulation is simulating coronal loop. I think this might just be like MHD turbulence in solar-like conditions. But I would have to go back to the setup to answer.
It may be missing the very important helicity.
Yeah. Right. So the first simulation that we studied in this work is infra simulation, which is simultaneously simulating the convective zone of the sun and the beginning of the solar corona. And what you see here is basically the magnetic field lines. This is a very expensive simulation. So once again, this cutting edge technology is allowing us to studying these very interesting simulations. And we can start asking the question, well, if you look at magnetic reconnection, it's not really magnetic reconnection in those simulations, but if you look at where the magnetic energy is diffused or converted into heat and kinetic, you can start asking the question, are we seeing some self-organized criticality behavior in those simulations? But first, you need to define the way to see where the magnetic reconnection is happening. So the method we used in this study is basically we started by defining a physical quantity where we think that magnetic reconnection might be happening. So this here we decided to use J over B, which is one of the common ways to identify places in the simulation where ohmic dissipation is happening, but we could have chosen another one. And then by applying a threshold, you can basically find these, yes?
J over B in sense of magnitude of J divided by magnitude of B?
Yes, yes. You're right. And basically by applying a threshold, you can find the maximums of these zones, and you can define these zones, right? And then you can do some labeling. So you can basically identify all these zones and study how they evolve through time, through the simulation, to study how much magnetic energy they're able to dissipate through their lifetime. So this is like a picture of these, the green patches are the zones identified in the Bifrost simulation. And what you can do with this is, if you're able to say how much energy is dissipated by these zones, you can reconstruct this power law that we had before. So this is the first result that we obtained, where for the Bifrost simulation, basically you can construct this dissipated energy, and you find again this power law that we had before with the self-organized criticality models and the sun. And I need to put some emphasis on the fact that this is more than 8 order of magnitudes for the power law. So it's like a very robust power law in dissipated energy, and this is in the duration. So you also expect the power law to emerge from the duration of the lifetime of the zones. So you have very few zones that last for the whole simulation, but most of them basically only last for one snapshot. This was our first result with this study.
Is it just straight MHD, or it is compressible, or what?
Okay.
Yes.
Liquid relative transfer. And there are many, there are many zones within the population. There's top of the convection of the and then condition for
yes. Yes. This I forgot to mention. This zone is high beta, and this zone is low beta. I can show you the numbers at the end. But these are very different regimes, right? And what I'm showing here is only for the atmosphere, or only for the low beta region in the simulation. Yes.
Looks like there's another power law.
Yes, exactly. So this basically, when you look at these zones, they're mostly comprised of zones of only one cell. So it's maybe a side effect of our numerical methods, but you would expect that if you increase the resolution of the simulation, this power law here would probably extend, and you would always find a fail basically because of the method we use. But you're right that there seem to be some like maybe another power law here, but it's only for 1 or 2 orders of magnitude, so we didn't really look into it.
Maybe I understand things wrongly. Are you saying that this power law has 8 decades?
Oh, no. This is in dissipated energy. It spans 8 orders of magnitude in the dissipated energy. So like in the ohmic dissipation. And for the duration, it's only 2 orders of magnitude. So the simulation we used was a solar hour.
That's fine, but this one is by 8 orders of magnitude.
What I mean is that the zones that dissipated the most energy dissipated 1 million times, or is it 10 million times more energy than the ones that dissipated lesser amount of energy.
But your x-axis of scaling is not even in decade, right?
It's in log, sorry.
10 to the 20 to 10 to the 20.
Yeah, so this is 28, and this is, well, 21, 22, so maybe seven orders of magnitude.
Really?
Yes. That staggered us also when we found these results at first. All right, so we were very happy with these results, obviously, but the first thing we thought is, well, maybe it's a fluke, right? Maybe it's a byproduct of the simulation we used or the methods we used. So the first thing we wanted to check is, can we also find this in other MHD simulations, right? So we decided to go for a very simple setup in Pluto. And this is basically just a magnetic dipole where we twist the foot points of the field lines. Very much more simple setup, but you also have a setup that is in a low beta environment. And basically we wanted to see if we would find similar results in the magnetic energy dissipation. And the answer is yes. Not only you also find magnetic, you also find this power law on multiple orders of magnitude. So in green, so the pentagons here, this is the Pluto simulation. This is the beta simulation I was showing you before in orange. And then I also plot here the convective zone, so the bottom part of the beta simulation, which also has a power law. And one of the main things that we found here is that not only you find it again, but it has about the same slope, which is also hinting at the universality of the process in MHD, which means that what we're seeing here is more related to the physics than to the physical setup that we use, right? But this is very important. The convective zone also has a power law. And basically what this means is, it's not because you have a power law that you have self-organized criticality, right? Turbulence is also able to generate these power laws. And the convective zone, we expect to find a lot of turbulence there, right? But we don't necessarily have all the ingredients I was telling you before for self-organized criticality. So to be able to really decipher if we're finding really self-organized criticality in these simulations, we needed to go further.
Just to be sure, the simulations and the results that you got with Pluto are not based on the region detection algorithm that you showed for the
yes, it is the same region detection algorithm. Okay. Yes, but we also checked that if we change the threshold, we found similar result. The method is robust to a change of threshold, but obviously if you increase your threshold a lot, you find fewer bigger zones. So the statistics of these slopes can change a little bit, but it's robust to that too. How much time do I have left? Okay, thank you. Cool. So is this proof of a self-organized criticality? Not really, but it's still very encouraging. So the next thing we wanted to do is to basically look at literally how these zones evolve through time, because that's basically how you can find out if it's just turbulence or self-organized criticality or like percolation, differentiate between all these systems. So here is a video to show you one of these zones in the convective zone of the beta simulation evolving. So all these cubes are cells where the physical quantity I defined before exceeds the threshold. So the magnetic reconnection could be happening in these cells. And the yellow cells are basically new active cells. So cells that they exceeded the threshold at the time iteration we're talking about. So this is like the evolution of a zone in the convective zone. And then I show side by side a zone in the atmosphere. And as you can see, the evolution in the atmosphere is a little bit different. It starts very small and then basically starts expanding. It's somewhat what you would expect from an avalanche model. But in the convective zone, the picture is a little bit different. And so how can you basically quantify this? Usually what people do is they use something called the spreading exponents. And so what is a spreading exponent? Well, this is very simple idea where you could measure the growth of your structure by fitting a power law to the size of a zone in a function of time. So the spreading exponent sigma here tells you how your zone grows through time. And I have, and basically the value of this spreading exponent allows you to distinguish between these classes of growth processes. It's something that is done widely in the literature. And I'm going to show you two very small examples of this. So this is just a toy model where you have an active cell in a 2D grid. And basically, at each time step, there's a random chance of this active cell to activate its neighbor. I'm going to show you the video. And you can measure the size or the number of active cells through time and fit lines through it. And this is what you find. And the index of the slope is the spreading exponent. And what is very interesting in this little model is that the slope seems to be the same one for all the models, even if you change the probability of basically contaminating your neighbors. And then to go back to forest fires again, this is just another example, but the difference is if a node has been activated once, it cannot be activated again. And once again, you find these spreading exponents for the forest fires example, but note that if the probability is low enough, well, you won't be able to spread, the fire is just going to die down. So this just toy examples to get intuition for the spreading exponents. So if we go back to these two examples, so convective zone versus atmosphere, this is low beta environment, this is high beta environment. This is what we found. So in orange here, this is the spreading, the spreading exponent for the size of zones in the low beta atmosphere, the Bifrost simulation. On top green, you have this is the Pluto simulation. And then on the bottom here, convective zone of the Bifrost simulation. So just by seeing this, you can basically get an intuition. In the convective zone, usually the zones start quite small and they don't really grow that much. They stay about the same size. Whereas in the atmosphere, low beta, the zones really start expanding in power law behavior. And then somebody could ask, well, what about sandpile model? What about something you know about this SOC, right? What would it look like on this plot? So we plot it side by side. This is what you find for classic avalanche model. You have a behavior that is very similar to the ones of the low beta in MAG simulation for the Bifrost simulation and the Pluto simulation. So this result is very interesting to us because it seems to be indicating that the low beta environment in MAG simulation are consistent, where the dissipation of magnetic energy is consistent with self-organized criticality, whereas in the convective high beta zone, the picture is not that clear. So this was very interesting for us. All right, so I think I'm going to go to my conclusion now. I think what I want you to remember is that self-organized criticality is found in a multitude of natural phenomena. We think that it might be explaining solar flares, but this question is not answered yet. But we found that in MAG simulations, the dissipation processes are described by power laws, very robust power laws, and that the dissipation events in low beta regimes, like in the solar corona, are consistent with self-organized criticality, but the picture is not as clear for the high beta regimes. Thank you very much.